Welcome everybody. We're going to do an experiment I call the distracted driver. This blue car represents the distracted driver, our texting, drunk, sleep-deprived driver. They're going to come down a hill and smack our innocent victim. So there's our collision. What we're going to do is we're going to manipulate the driver mass. That is, how much stuff the blue car is made of. And we're going to see how that affects the change in velocity of the distracted driver during the impact. So, the math teachers call the independent variable, that is the manipulated variable, x, and that's our driver mass. And the math teachers call the dependent variable, that is the responding variable, y. We're going to find the change in velocity of the distracted driver by taking the final velocity and subtracting the initial velocity. So the initial velocity is how fast the car is going right before impact, and the final velocity is how fast they're both going after the impact. So how are we going to do these calculations? Well, before the impact, the distracted driver is on a ramp, and the velocity is constantly increasing on the ramp. So, if you know how far the driver moves, and if you release from rest, and you know the time it takes to move a certain distance, you can simply find distance over time, and that'll tell you the average velocity. Now, we don't want the average velocity, we want the final velocity, that is, how fast the driver is going right before the collision. So, if the velocity is constantly increasing, the final velocity is double the average velocity because we're releasing the distracted driver from rest. When the collision begins is when the acceleration ends. When Friday night ends, Saturday morning begins. And that's sort of the confusing language surrounding this. The final velocity for the ramp is the initial velocity for the collision. So, how are we going to find the final velocity? Well, after the collision, the two cars move with a constant velocity, and you may notice the little piece of paper under here. In order to counteract friction, this flat portion of track is in fact not flat. It's just a little bit inclined downhill to the right here, and that'll cause them to move with a nice constant velocity after the impact. So, because the driver slows down, the final velocity is less than the initial velocity, and therefore we're going to get a negative change in velocity for the distracted driver. As usual, we're going to organize our measurements and our calculations into a table. Think of a descriptive title. Traditionally, the manipulated variable goes on the left-hand side. Don't forget your units. All of the important measurements and assumptions go in the middle, and then the responding variable, the dependent variable, goes on the right-hand side. Try to predict what shape this graph is going to have. As usual, the x, that is the horizontal axis, is the independent variable. The y is the vertical, the responding axis. And try to predict what shape this is going to have as the driver mass gets greater and greater. As we increase the mass of the distracted driver, what's going to happen to their change in velocity during the collision? Going beyond a shape, a graphical prediction, you can make a proportional prediction. So if you double the driver mass, how is the original change in velocity going to change? Is it going to be half the original change in velocity, double, a quarter, 4 times? Can you think of a model that will predict the proportional change in velocity as the driver mass increases? So, that's your experiment. Enjoy, and I'll see you in the analysis video.